Hi, this is Ms. Fitzmaurice, and this video is an explanation of free response problem number 7. That's on page 13 of your review packet. In 2001, when this exam was being taken, I was in 8th grade. In May of 2001, space tourist Dennis Tito returned to Earth. So that was the first ever space tourist. And this information about space tourism is relevant to this problem because this is a problem about Jupiter. Okay, so the problem reads, an explorer plans a mission to place a satellite in circular orbit around Jupiter, which has a mass of 1.9 times 10 to the 27 kilograms and a radius of 7.14 times 10 to the 7 meters. In part A, they just want us to do algebraic proofs. It says if the radius of the planned orbit is r, use Newton's laws to show each of the following. Okay, so we need to think about what this satellite would be doing. So here's Jupiter, and here is our satellite. And the satellite is moving around Jupiter, hopefully in a circular orbit. And since it's kind of out there in the middle of nowhere, that's the only force that's going to be acting on it. So we have FG J, the force of gravity from Jupiter on the satellite. Now, because this satellite is moving around in a circle, we know that its acceleration is going to be mv squared over r. So let's go ahead and write out Newton's second laws. Newton says sigma f equals ma. Okay, who knows what direction this is in? I'm just going to say x for now, but we're in the middle of outer space, so what's right or left or up or down? Okay, and so we have Fg from J, or gravitational force from Jupiter, is going to be the mass of the satellite times acceleration of the satellite, which is Vt squared divided by r. Okay, and remember, at the beginning, we're solving for this Vt. Okay, so we can use our universal gravitational Gmj, that's the mass of Jupiter, times little m, divided by r squared equals mvt squared divided by r. We're able to cancel a couple of things out. This squared cancels with this r. And now we have Gmj over r equals Vt squared. Remember they told us actually that it should be capital R. That's our orbital radius. So I'm going to replace the little r's with a capital R. And when I take a square root, I get Vt is equal to the square root of Gmj divided by r, which is actually what they asked us to prove. So that was part I. In the second part, it wants us to find t, and t is the period of the satellite. To think about this, we remember that Vt is equal to 2 pi r divided by t. And so we can go ahead and use that, and we can actually plug this in for Vt. So we can write square root of Gmj divided by r is equal to 2 pi capital R divided by t. Okay, I'm going to go ahead and I'm going to cross multiply because I want t on top. So I end up with t is equal to 2 pi r times the square root of r divided by g mj. Okay, now we've actually solved for t, but in our answer, everything is inside of the square root. So we know to bring 2 inside of a square root, we have to make it a 4. So I'm going to do that. I'm going to get rid of that 2, bring it inside the square root, and make it a 4. If I bring pi in, it has to become pi squared. And if I bring r in, it has to become r squared. Now I can go ahead and simplify. So I have t is equal to the square root of 4 pi squared. I'm going to combine my r's. I have r and r squared, so that becomes r cubed divided by g times mj, and that's exactly what they wanted us to prove. Right. So part B says the explorer wants the satellite's orbit to be synchronized with Jupiter's rotation. This requires an equatorial orbit whose period equals Jupiter's rotation, so like Jupiter's day, which is 3.55 times 10 to the 4 seconds. Determine the orbital radius. Now we can do that using what we solved for in part A. So we know that t is equal to this. We have numbers for g, mj, and r, then if we have numbers for t, mj, and t, then we can solve for r. Okay, so I'm going to go ahead and write this equation one more time. We have t equals 4 pi squared r cubed divided by gm, and that's m Jupiter square root. Okay. The thing we want to probably do first is solve for r. So first we have to get it out of the square root. Okay, to get it out of the square root, we square both sides. So we have t squared is equal to 4 pi squared r cubed divided by g times mj. Okay, we want to isolate r, get it by itself, so I'm going to multiply both sides by g mj. And then I'm going to divide both sides by 4 pi squared. Okay, so now I have r cubed by itself. The last thing I need to do, and you've all seen this in algebra at some point, if you had b cubed equals 5, to solve for b, you raise everything to the 1/3 power, and you could say that the 1/3 canceled the cubed. Okay. So we're going to do the same thing. So I have I have r cubed equals g mj t squared divided by 4 pi squared. I'm going to take everything to the 1/3 power. Now 3 times 1/3 is 1. And I get r is equal to the cube root, or to the 1/3 power g mj t squared divided by 4 pi squared. Okay. Now the hard part comes in. We have to actually plug this into a calculator. And if you don't get it, try it a couple of times, but you should end up with 1.6 times 10 to the 8th and remember this is in meters. Alright, in part C it asks us to imagine that the satellite is either too fast or too slow to go around in a perfect circle. So it's asking us what's going to happen. Now, if our satellite, we have to remember that we have a certain amount of force pulling this thing in. And if it's exactly right, it'll go around in a circle. Okay? Now, another way of saying that the satellite is too fast is to say that to be equal to gravity is that gravity is too weak. Okay, and what you can imagine is that if gravity is too weak, this thing will actually go out further than a circle, and you'll get kind of an egg-shaped orbit outside of the circle. Okay, so gravity is too weak. If it's too slow, quote unquote, what that means is gravity is too strong for it to go around in a complete circle, and so gravity's going to pull it in tighter, and you'll get an oval on the inside of a circular motion. So, too strong. Okay, in terms of points, you got 1 point if you wrote Newton's second law at all. You got 1 point if you knew that the only force involved was g mj m over r squared. You get 1 point if you actually solved for Vt, and 1 point if you actually, through your algebra, solved for T. In part B, you get 1 point for solving for R algebraically, and 1 point for the correct answer. If you were just able to get the correct answer, and you did that without directly solving for R the way I did it first, give yourself 2 points still. But even if you plugged in all the numbers incorrectly, give yourself a point for solving for R. Finally, you get 1 point for this egg outside of the circle, and 1 point for giving a good reason, like the gravity is too weak, 1 point for an egg shape inside of the circle, and 1 point for some sort of reason like gravity is too strong.